So what we're going to talk about now is Java ReentrantLock. And you'll see that Java ReentrantLock, just like all the other synchronizers in Java that use abstract queued synchronizer, is basically just a wrapper around the abstract queued synchronizer framework doing the semantics for reentrant locks. And when we see semaphores, you'll see that it's basically the same thing. It's a wrapper around abstract queued synchronizer. So it's pretty cool. Abstract queued synchronizer is really the workhorse of everything under the hood. OK, so to understand reentrant locks, we have to take a step back and talk about the concept of a mutex. And I'll probably rearrange this at some point, because this topic probably should come a little bit earlier before we get into the other topics. But a mutex, or mutual exclusion, is a type of lock that ensures exclusive access to a critical section. So what that means is there's only one thread at a time that can be waiting. If you take a look at this link, you'll find out more about mutual exclusion. So we have a queue of waiting threads, or let's assume for sake of argument, some thread comes along, and that thread attempts to acquire the lock. As long as the critical section is not in use, then the lock acquisition will succeed, and that thread will be then waiting, or running rather, and other threads will be waiting for their turn to get a chance to go. Why do we do this? We do this, of course, to avoid race conditions. Race conditions occur when an application depends on the sequence or timing of threads for it to operate properly. So very, very subtle sets of things. Lots of problems can arise. More on race conditions here. Typically, mutual exclusion is sort of the most fundamental way of doing locking. And it's usually implemented by some kind of atomic hardware mechanism. And if you recall from our discussion a little earlier, atomic meant it appeared simultaneous, or it appeared to be not simultaneous, instantaneous from the perspective of the system. And it either succeeds completely or it acts as if nothing happened at all. So that's why I said the transporter beam is a good example of that. A properly functioning transporter beam is atomic, right? You either get beamed to your destination or you don't leave. You don't beam like part of you, right? That would be a problem. This is called linearization or atomicity or stuff like that. There are two common ways of doing this. If you take a look at Wikipedia, you'll find there's lots more ways, but these are some of the common ones that are built in to hardware. Now, back in the early days of computing, before we had multiprocessors, people typically implemented atomicity by masking or changing interrupt priority levels. So you could say, I'm not going to let, I'm going to mask all the interrupts to do my work, and I'll have atomic access, which has a lot of problems. Most notably, it doesn't scale to multiprocessors. So on uniprocessors, that sort of worked. Even there, it was problematic for a variety of reasons. So what people started to do is they started to build this stuff into the hardware. And by the way, this follows a very, very time-honored tradition we see all the time. Stuff becomes useful enough at the software level, and eventually people find a business case to put it into hardware. And you see that all the time. That's not an uncommon state of affairs. So the first mechanism we're going to look at is something that's called compare and swap. You can take a look here for more about this. I'll show you how it works. I'll show you how it's used first, and then we'll talk about how it's implemented. So the way it works is you come in here, and lock basically goes into a loop, and it does a compare and swap on some location in memory, which is being treated as a lock, but it's just an int. And it says, if you're 0, set yourself to 1, and tell me what happened. And so, and it'll return the old value. So what it's going to do is if it was unlocked, it will lock it and return the fact it was unlocked. So that's the state change that you need. Here's unlock. Unlock comes in some magic atomic mechanism works that's done in the hardware, and it basically sets the location to 0. So that's how you release. That's how you unlock. And this is how you lock, right? You spin. This is basically an example of spinning. There's a canonical, sort of C-like way of doing compare and swap. Now, keep in mind that, it's probably not written in C. It's probably written in assembly code. Or there's probably an instruction called, compare and swap that is written in the instruction logic of the processor. But logically, here's what's going on. It comes in here. There's an atomic region. The current value of the lock is stored in a variable that's local. We check to see if the old value equals the value that we're asking about, this guy. So we're basically saying, are you unlocked? If you are unlocked, set the location to the new value. So now we're locking it, right? So we're setting it to 1. 1 means locked, 0 means unlocked. And we're returning the old value. So this thing will keep returning 1 as long as the thing is locked. And when it returns 0, that meant we found it to be unlocked, we locked it, and we found out it was unlocked before. So now the state has changed. Any questions about that? OK, now the thing to remember is this is always done in hardware. It's super duper optimized. I'm just showing you kind of logically how it works. The other thing to note is if you wrote a program to do locking that only did this, what would happen? What would be the consequence of doing that?
One, it would just be spinning.
It would spin, right? Unless there was no contention, right? So if there's very little contention, then it won't spin for very long. It'll grab the lock right away. If there's a lot of contention, it'll spin, and that's probably a bad thing unless you're doing a nuclear reactor, temperature control monitor thread or something like that, where you really, really want to know instantaneously that the values have changed. OK, so that's compare and swap. Here's the other approach. This is called test and set, which is actually, in my mind, sort of like a lobotomized compare and swap. So what you do here is you call lock, and lock spins while test and set returns 1. You continue. Same basic idea. 0 means locked, 1 means, 0 means unlocked, 1 means locked. Here's test and set. You come in and you read the current value of the lock, and then you set the lock to locked, and you return the old value. So this is a little, it's very similar to compare and swap, but it's not quite as general. What this is saying is read the old value and lock the new thing. So you're always locking, locking, locking. And if for some brief instant of time it had been unlocked and you call it, you'll get back the fact it was unlocked. So when this thing returns 0, it had been unlocked and you just locked it. So now you've got the lock. So those are the two operations. Any questions about that? Now, mercifully, we don't have to program at this level of abstraction, right? This would be just such a nightmare. But Doug Lee had to program at this level of abstraction when he wrote all the stuff for the Java library. But that got abstracted away from us by the rest of the abstract queued synchronizer framework. We always love human known uses for everything. So here's the human known use, the airplane, restroom. And the model here is if you want to go in the restroom, you have to wait for the sign to be vacant. You come in, it changes state to occupied. If people come along, they have to queue up. And then when you're done, you leave, and someone else can come in as long as the thing is vacant. Right? So that's the metaphor to keep in mind when you're thinking about mutual exclusion. All right, any questions about that general concept? All right, now let's talk about ReentrantLock. So now that we've given you the background, ReentrantLock is part of Java, and it implements the lock interface. And most of the implementation is written in Java, which we'll look at in a minute. There are some parts, though, that are written in the unsafe libraries that we were just talking about. And those are native implementations in C or C++, which, of course, themselves are implemented in the hardware, right? So those calls are using hardware-level calls. And this is a very interesting article that explains what's in the unsafe libraries, because there's really no other documentation other than reading the source code. So this guy once sat down and explained how it all works. It's actually quite interesting. If you want to learn concurrency, low-level concurrency things, read his article. It's very good. All right, uses the bridge pattern. We talked about that before. Don't have to talk a lot about that. The key methods in a ReentrantLock, surprise, surprise, are variants of lock and unlock. I know that comes as a surprise, but that's what they basically do. And as you can see here, these methods are defined in the lock interface. So ReentrantLock implements lock, and it also implements Java I/O serializable. So this maybe goes back to the question from before. We're combining multiple interfaces together, which we could make another interface from that if we wanted to, by the way. And the methods simply forward to their implementations because they use the bridge pattern, right? So here we have lock, lock interruptibly, unlock, and so on. and then those things just forward on down to the implementation using the bridge pattern. Lock acquires the lock if it's available. And if the lock is available, that's easy. You get it, right? We'll look at how it works in a minute. If the lock is not available, then the way we wait for the lock depends on the synchronization policy. So if we had fair versus non-fair, that's going to differ how we're going to treat this thing. If we have fair semantics, then it's basically going to do the classic specific notification stuff that we talked about. If it's not fair, it's going to use some more optimized way of doing things. And that's all handled for you by the underlying abstract queued synchronizer framework. Non-fair implementations are optimized in hardware. They do a little bit of spinning, but they're not pure spin locks. Now, here's something weird. Something went wrong in the Java community at some point. Somebody got confused, and they made the default behavior for ReentrantLock to be uninterruptible, right? And so if you wanted to have your lock operation interruptible, you had to have something called lock interruptibly. But then when they did the condition variable stuff, they did it the other way around. So you have await, which is interruptible by default, and then you have await uninterruptibly. So it's always very confusing. Bottom line is that lock interruptibly acquires a lock unless the thread is interrupted. In contrast, lock is not interruptible. So lock will not be interrupted. It'll just wait in perpetuities, which is sometimes good, sometimes bad, right? Unlock attempts to release the lock. Now, what does it mean to attempt to release a lock? Well, it may be the case that you don't actually own the lock, and you're trying to release a lock you don't own. So if you try to release a lock, and either the lock is not held or you're not the owner of the lock, then it's going to bail out and throw an exception. And it throws the illegal monitor state exception or something like that. It's a similar exception you get in other situations as well. There are a bunch of other ReentrantLock methods which we'll look at in just a minute. Another interesting thing about ReentrantLock, it supports so-called recursive mutex semantics. As you know, what that means is if you are the one who own the lock, you can reacquire the lock. So here's a visualization of how this works, which, by the way, if you want to learn more about ReentrantLocks, take a look at reentrant mutex or recursive mutex, basically the same idea. So what you can do here, we have a lock that's currently, it's not held. You call lock, the hold count sets equal to 1. You call lock on yourself, the hold count goes to 2. That's basically what it means to be a reentrant lock. ReentrantLock is very similar to Java built-in monitor locks. It's got lock and unlock, which is pretty much like synchronized methods or synchronized blocks. That's just syntactic sugar around almost exactly the same construct. However, ReentrantLock has some additional stuff. So it has lock interruptibly, so you can let locks be interrupted, whereas locks by default in monitor objects can't be interrupted. It has try-lock, which we'll talk more about in a second, and it has both non-blocking try-lock and timed try-lock. And those actually have subtle different semantics. Now here's a little piece of fun trivia. The non-timed version of try-lock, that's this guy here, ignores the fairness policy. So you could have said, I want this ReentrantLock to be fair, and everything else, whenever you call acquire, it'll be fair. It'll go to the end and wait. Try-lock, however, is not fair. And so if it's possible for try-lock to get access to the lock because the lock gets released, it'll grab it even if there are other things waiting to go. If you want to have fair try-lock semantics, you need to call try-lock with a 0 timeout. And then that'll make you wait at the end if you can't acquire it right away. There's a little explanation of that if you read the comments in the code, but it's not the most obvious thing to remember. OK, what I'd like to do now is show you an example of using ReentrantLock, and then we'll look at the source code. So the example of using ReentrantLock, we're going to use something called ArrayBlockingQueue, which we're going to use for a bunch of different examples. ArrayBlockingQueue basically is a bounded blocking. It's a blocking bounded FIFO queue. And how do we know it's a bounded blocking FIFO queue? Well, ArrayBlockingQueue extends something called abstract queue, which gives it its queue operations. and it implements the blocking queue interface, which gives it the ability to do these blocking operations like put and take. And you can look at the source code. We'll look at some of the source code here in a second. We're just going to look at a little tiny piece of this code. We can come back at some other point and look in more detail. It's a very cool class. But we're going to look at just the parts that have to do with the use of ReentrantLock. We'll come back later and look in more detail at how it works. So basically, here's the implementation. It uses a ReentrantLock. And it uses this in lieu of the Java built-in monitor object. It doesn't use Java built-in monitor object because they wanted finer level grain control over how things worked. And it's super duper optimized. Remember we talked before, if you use the built-in monitor object, what was one of the downsides with the Java built-in monitor object? Do you remember?
You can only have one queue.
You only had one wait queue. And this thing's going to have multiple queues for people who are waiting for it to be full. People are going to be waiting for it to be empty. It's actually super duper cool. There's even more cool stuff we'll look at even later about something called a linked blocking queue, which is even more interesting. Then there's a bunch of other state in here, which is the object state that's protected by this lock. So the queue of items, or the vector of items, the array of items, sorry, whether you're putting or getting, where you do the next put and get, how many items there are. These are all the data that needs to be protected. And these do not have to be defined as volatile because they're protected by the mutex, right, or by the ReentrantLock. OK. So here's how this works. I make an array blocking queue of a certain size. And actually, I need to fix that because I can just make it a queue. And I come along here and I do a take on this thing. And T1 is going to do a take. As you can see, if you watch the left-hand side, that's kind of what's happening. It starts out with a hold count of 0. And so when we come in here and we call lock interruptibly, then that's going to go ahead and transition this thing to the locked state. So the lock is now locked. And the hold count equals 1. And now somebody comes along and calls take. And that's going to come in. And it's going to go ahead and basically remove the item, which we're not showing at this point. We're going to show that later. And that's going to unlock the lock. And that's going to set it back to 0. OK. There's some other stuff that's going on here, too, which I don't show. This is how you wait when the queue is empty or full. And we're not going to talk about that. That's going to be talked about when we talk about Java monitor objects. It's something called the monitor object pattern. OK. There's a bunch of things to think about when you program a ReentrantLock. ReentrantLocks have to be fully bracketed. Very important. Fully bracketed means the thread that acquires the lock must be the one to release it. That's what it means to be fully bracketed. So the same thread acquires a lock is the same one to release it. This is also known as the scoped locking pattern. It's described here in a paper I wrote. It's also in the POSA 2 book. And you see this very commonly in C++, where you have constructors and destructors. Here's an example of C++ 11 mutexes, which are basically C++ 11 locks, just like a ReentrantLock in Java, very similar to ReentrantLock in Java. And you see you can come in here and you have a constructor called a lock guard, which goes ahead and acquires the lock. And then this piece of code will be running in mutually exclusive manner. And when it's done, the destructor of lock guard gets called, and it releases the lock. So that's also an example of something that's called the resource acquisition is initialization idiom, which is a common thing you see a lot in C++, where the constructor acquires the resource and the destructor releases it. ReentrantLocks are very simple, but they're also somewhat error-prone, just like so many other things that are simple, like assembly code. Assembly code is easy to write any given line, but writing lots of lines is hard because each individual line is very simple, but the composition is difficult. Here are some of the problems you run into. A common problem is acquiring the lock and then forgetting to release it on the way out, which means that the lock is still held, and you can't unrelease it unless you do some other crazy, wacky things. This is why it's always a good idea to use that try finally idiom we talked about before. Another problem is sort of the opposite, releasing the lock you never acquired. Now, in this code, it would be pretty monumentally silly to comment out the lock, right, in the lock operation. You would very rarely do that. But if you had a complicated piece of code with if statements and loops, it's all too easy to forget to do the original lock. Another mistake is to hold the lock for a long time. Here we grab the lock and then do something in a loop that doesn't require the lock, and we're holding it for a long time where we didn't really need to hold it the whole time. And then the final thing is to access a resource without having the lock held at all. So here's a place where we have a critical section, but we didn't acquire the lock, and so multiple threads will be contending and smashing into it with race conditions. Reentrant locks are used all over the place in Android, but particularly in the concurrency libraries. All right, the last thing I'm going to do today is very quickly go through some of the ReentrantLock code. And this is what the class design looked like. And lo and behold, this looks very, very, very similar to the simple semaphore example we looked at before. You have ReentrantLock, which is the abstraction in the bridge pattern. You have the sync class, which is like the implementer hierarchy's base class. And then you have fair sync and non-fair sync. And those are the concrete classes in the bridge pattern. And oh, by the way, sync inherits from abstract queued synchronizer. Right? So that's got that whole pile of stuff up there. And we'll see some of the interesting methods here in just a second. So here's ReentrantLock. And here's the abstract static class sync, which is an abstract queued synchronizer. And here's its lock method. It defines the lock method to be abstract so that the fair and non-fair versions can be different. It's kind of cool. It also defines something called non-fair try-acquire. And this is actually an interesting example because it illustrates how you do recursive lock semantics. Non-fair try-acquire checks to see what the current thread ID is. And then it checks to see what the current value of the lock is. And if the lock is unlocked, so keep in mind, this getState call is fine. GetState is accessing a volatile data member, so it can read it, no problem. We know whether it's 0 or 1. But between the point when we found out it was 0 and we checked to see if it's 0, it may have gone to 1, right? It may have become locked. So now we're going to check to see whether or not it's still 0. So we call compare and set state with 0 and acquires, let's assume, is 1. So if it turned out that, in fact, we were able to set this thing to be locked because it was uncontended for, we become the owner and we're done. So that's basically how to do a very quick lock using a low-level hardware primitive. Otherwise, if we're the owner of the lock, right, so the current thread is us, then we simply go ahead and set the state to be incremented by 1. So that's an example of a recursive lock. So we're acquiring a lock that we already own, so we just increment its count. So those are the two cases. Otherwise, we didn't manage to acquire it. It's not available for acquisition at this point. Here's try release. Try release basically takes the current state and how many releases we're doing. Let's assume it's just 1, so it's going to go down by 1. If we're not the current owner of the lock, then it's an illegal monitor state exception, right, because somebody was trying to release a lock they didn't own. Otherwise, we basically say nobody owns this lock, and we're going to set its state to 0. And there's a bunch of other methods to check to see whether it's held exclusively, blah, 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 blah. Skip over all these things. All right, here's non-fair sync. So non-fair sync extends sync. Its lock method, oh, by the way, the lock method on ReentrantLock just turns around and calls the lock method on whatever the synchronizer implementation is. So lock, in the non-fair case, checks to see if it's unlocked and tries to lock it using the compare and set operation, the compare and swap operation. And if that works, we're done, right? We got the lock. Otherwise, we call acquire. This acquire is calling to abstract queued synchronizer, and that's going to go through that whole process of basically doing the specific notification pattern. So we take one shot at trying to get this thing locked without blocking, and if that works, we're done. If there was contention, we basically go ahead and wait. So this is sort of an adaptive lock. We try a little bit to get the lock, and we give up very quickly if we can't make progress. Here's try acquire. Try acquire just does the non-fair try acquire. Here's the fair version. So check out. Remember, here's non-fair. So non-fair's lock basically first tried to barge ahead and get the lock, because that's what you do if it's non-fair. You don't care. If it's available, I'm going to grab it. I don't care who might be waiting for it. I want to get a shot at it first. In contrast, fair's implementation of lock just goes ahead and says, all right, I'm doing specific notification. If there's nobody contending for it, maybe I'll get it. Otherwise, I'm going to wait my turn. Here's try acquire. This is the fair try acquire. So in fair try acquire, basically, if there's nobody waiting, then we go ahead and try to grab the lock. But there's somebody waiting, we are nice and we don't try to grab the lock. And again, it also implements the reentrant mechanism. Here's the constructor for ReentrantLock. As you can see, it just makes a non-fair synchronizer by default. Here's the one that takes the fair parameter. So you can see it either makes a fair or non-fair implementation. And then all the other methods, what I showed you was the bulk of the implementation. Pretty much all the other methods just delegate to the implementation version. So you can see that they're all just basically forwarding via the bridge pattern. So if you kind of get a feeling for this, we're almost done. Go back over here for just 1 second. Basically, all the heavy lifting is taking place in abstract queued synchronizer, which we looked at before. The code here is delegating, or actually the code here is delegating through the bridge pattern to either the fair or non-fair version. And these guys are basically adding a little bit of window dressing on top of the stuff that abstract queued synchronizer provides for you. OK, any questions? So you now know way more than pretty much anybody else on the planet about how ReentrantLock and abstract queued synchronizer are implemented in Java. But the good news is everything else we'll cover is at a higher level that builds upon the things we talked about today.